In question 23, we're asked, in the course of solving an equation, which of the following procedures can result in an equation that yields a real root that does not satisfy the original equation? So, which of these procedures can give a solution that is not or does not satisfy the original equation? And what we're talking about in this case is what is called an extraneous root or solution. And answer A is subtracting the same number from both sides of an equation. Well, that will always yield an equation, or that will always yield a real root that satisfies the original equation. Raising both sides of an equation to the third power, squaring both sides of an equation, answer C, and dividing both sides of the equation by a non-zero number, D. So A and D are pretty clear. As long as we're not dividing by zero, we can divide both sides of an equation by the same number, and we will still get an equation that is that has the same roots as the original equation does. Now, for C, there's something that you need to remember here from Algebra 2, and perhaps it would be best to just give an example of this. If we were to take the equation square root of x plus 4 is equal to x minus 2, the way we would solve this is to square both sides. And when we do this, we're going to end up with x plus 4 on the left and x squared minus 4x plus 4 on the right. When we set this equal to 0, or collect all the terms on one side and leave 0 on the other side, we simply end up with x squared minus 5x, which factors to x times x minus 5, which then has two solutions, two real solutions. But we see that when we go back to the original equation and we substitute them in there, substituting x equals 0 into the original equation gives us 2 is equal to negative 2, which cannot be. And so that's an extraneous root. Substituting x equals 5 into the original equation gives us 3 is equal to 3, and so that is a solution that satisfies the original equation. So the process of squaring both sides of an equation can result in a real root that does not satisfy the original equation. But this doesn't happen when we raise both sides of the equation to the third power. And that is related to the fact that squaring a negative number gives you a positive number. Squaring a positive number gives you a positive number. Whereas raising any number, positive or negative, to the third power gives you a sign that is the same as the original number. For example, a squared equals 9 gives you two possible solutions. A could be plus or minus 3. So if we had started with a value a equals 3 and squared both sides, we would have gotten a squared equals 9. And that is true if we knew that a was equal to 3. However, if we only had the squared version of that, we would have had two possible answers, and we might not know whether we started with a equals 3 or a equals negative 3. On the other hand, if we had a cube, for example, a cubed equals 8, then a could only be 2. So if we had started with a equals 2 and we cubed both sides, we would get a cubed equals 8, and we would know exactly what the value of a had to be before we cubed both sides. And so it's a simple example that hopefully shows that cubing both sides, or raising both sides of an equation to the third power, does not produce an extraneous root, whereas squaring both sides could produce an extraneous root. And that's all for this video.